Welcome to this explainer. Today, we're targeting a very specific, high-stakes topic, Cambridge AS and A-Level Computer Science, subject code 9618. Specifically, we're zeroing in on documenting algorithms and flowcharts. Now, if you're gearing up for this exam, you already know this topic can be an absolute marathon. It's demanding, and it requires some serious mental endurance. But we're going to take the guesswork completely out of the grading rubric today. We're going to take the official insights directly from the principal examiners and transform them into a clear, actionable strategy that you can actually use.
So right off the bat, let's address the elephant in the room. What actually separates a B-grade candidate from an A-star candidate? Well, it's really easy to assume it's just about, memorizing more code or cramming in more textbook definitions. But surprisingly, that is not what the data shows. The academic benchmarks for this syllabus require something much deeper. They're looking for logical, structured reasoning. You see, top-tier grades aren't awarded just for recalling facts. They're given to students who have totally mastered the framework of algorithmic thinking. It's all about how you systematically analyze a problem and then pace yourself to present that solution clearly.
To get us there, here is our roadmap for today. We'll start with the exam differentiator, move on to the procedural framework, break down the method mark strategy, highlight the top examiner warnings, and finally look at evaluating algorithm quality. Let's jump right in.
Section 1, the exam differentiator.
Okay, so the assessment framework here explicitly prioritizes analytical depth over superficial breadth. What does that mean? Well, average candidates tend to show off this wide but very shallow pool of knowledge. They sprint through the basics and burn out. But top scorers? They build a solid theoretical architecture that rests on precise definitions and, crucially, causal relationships. Even more importantly, and this is a big one, principal examiner reports highlight that candidates who reference cross-topic connections achieve significantly higher marks. For example, explicitly linking your flowchart logic to how arrays handle data. It shows the examiner you understand the entire system, not just an isolated diagram in a vacuum. You're seeing the big picture.
Moving on to Section 2, the procedural framework. This right here is the standardized sequence you need to rely on every single time you tackle an exam question. Seriously, do not just start drawing shapes and hoping for the best. Think of this as your pacing strategy for the long haul. Step 1, deconstruct the question. Step 2, extract the relevant data and apply the underlying principles. Step 3, select your analytical framework. Step 4, execute your analysis with absolute clarity in your notation. And finally, Step 5, present it in the appropriate format using the exact correct terminology. I promise you, following this exact order acts like a guardrail. It prevents you from panicking and missing critical elements when the exam pressure is on.
Next up is Section 3, the method mark strategy.
This is a massive alert directly from the examiners themselves. They explicitly state, students lose marks by not showing working. Listen to me, algorithmic thinking requires step-by-step decomposition. If you try to just mentally jump straight to the final solution, like sprinting to the finish line without running the actual race, and you make one tiny arithmetic or logic error along the way, boom, you get a 0 for that section. But if you document your algorithm clearly, executing your analysis step by step with clear working, even if your final answer is completely, absolutely wrong, those method marks can and will save your grade. You are literally rewarded for the process itself. Please, whatever you do, do not leave these easy marks on the table.
Let's look at Section 4, top examiner warnings.
These are the top 3 traps pulled straight from the principal examiner reports. These are the hurdles that trip people up. Number 1, candidates constantly forget to check overflow and edge cases when documenting algorithms. Like, they completely fail to verify if a variable exceeds a maximum integer value. Number 2, ignoring boundary conditions. Sure, your flowchart might work perfectly for the middle-of-the-road data, but what happens at the extreme limits? You have to test the boundaries. And number 3, providing generic answers. The examiners desperately want answers specific to the context given in the question. If the question is about, say, a temperature sensor in a greenhouse, your variables and your logic must reflect that specific scenario. A generic textbook example just won't cut it.
Okay, I have a quick challenge for you to make sure you don't blank on these when you're sitting in the exam hall. Create a memory hack right now. Take the first letters of those key terms, overflow, edge cases, boundary conditions, context, and make a mnemonic that works for your brain. It could be something like only evaluate boundary contexts, or, I don't know, overlooking edges breaks code, whatever sticks. Write it at the top of your scratch paper the second the exam begins. That way, you have the built-in checklist to verify your work.
Finally, Section 5, evaluating algorithm quality.
When a question asks you to critically evaluate an algorithm's quality, they are not looking for a vague opinion. They are looking for highly specific technical metrics. You absolutely must identify the time complexity, meaning how long does this take to run as the data volume increases. You also need to identify the space complexity. How much memory is this in consuming? You must address those edge cases we just hammered home, and crucially, you have to explain their direct effect on overall performance. This is what evidence-based reasoning actually looks like in practice.
Because here's the secret. Top-scoring candidates don't just write, "Algorithm A is good." No way. They engage in deep evaluative thinking. They consider multiple solutions. They analyze the trade-offs. So maybe algorithm A is way faster, but algorithm B uses significantly less memory. You have to point that out. They acknowledge the limitations of their chosen design, and above all else, they justify every single decision with hard evidence derived directly from the problem statement.
And just a quick but vital note on comparative analysis, because this is another spot where candidates bleed marks for no good reason. True comparative analysis requires you to identify similarities and differences. You can't just list facts side by side. You have to use comparative connectives to actually link your points, support each individual comparison with evidence, and then draw a solid, logical conclusion about their relative importance. It has to be a fully balanced, structured argument from start to finish.
So I want to leave you with this final, somewhat provocative question. Are you leaving method marks on the table? Seriously, I highly encourage you to go review your recent past papers. Look closely at your working. Are you actually executing your analysis with clear notation? Are you pacing yourself and applying our 5-step procedural framework? The difference between a B and an A star is almost entirely in that structure and stamina. Dive back into those past papers, practice this system systematically, and master the process. You've got this. Thanks so much for joining me on this explainer.